happy to start the new semester with a talk by Alon Cohen from Tel-Aviv University, originally from GPU, afterwards Technion. And his work is mainly about online learning, reinforcement learning, things like that. And today he will be presenting about rate optimal policy optimization for linear Markov decision processes. In case you're not good.
Thanks, Moshe. Hello, everyone. So thank you for having me. So, as Moshe said, this is a talk about enforcement learning, specifically about linear Markov decision processes. Well, the loss function changes adversarially between episodes, and our result is an optimal rate of regret for this kind of model. So, first of all, reinforcement learning. I don't know how many of you really know about this, but the main difference from like classic statistical machine learning is that in statistical machine learning, usually we're trying to make predictions about something, right? We have some distribution about examples. Let's say we have a distribution about images, and we want to predict whether an image has a cat or doesn't have a cat in the image. In reinforcement learning, instead of predictions, we're making actions, and the actions sort of affect the environment, and they affect the examples that we're going to see in the future, and the loss that we're going to suffer in the future. Okay, so it's a different learning paradigm. It has many applications, such as playing games, robotics, different kinds of robotics, autonomous driving, probably, maybe Shai knows better about this than me, many other. So briefly, before I start delving about into the details and all that, we're going to consider an episodic finite horizon linear Markov decision process where the dynamics are fixed but unknown. And the losses, we have two models. Either they are drawn IID, so in every state action the loss is drawn from the same distribution, but the observation is what's called bandit feedback, so we only observe the loss of the states and actions that we traverse through. This is one model. The other model is adversarial full information. So here the losses are chosen by an adversary, but we observe the loss of all of the state actions simultaneously at the end of every episode. And the algorithm that we're going to show is based on policy optimization. If you know about RL, it's going to say something for you. If you don't, then forget about it. And we're going to show a regret bound that's optimal in terms of the number of episodes, which is k. So I'm going to, in the talk, I'm going to give a brief introduction, then I'm going to explain what the model is specifically. I'm going to talk a little bit about prior work, present our results, and then most of what's going to happen after that is a lot of technical background. And then after that, I'm going to give you a brief idea of the proof in our paper. By the way, I didn't say the paper is with Uri Sherman, Tamir Hazan, and Yishay Mansour. It was just accepted to ICML. Okay. So the Markov decision process is comprised of a set of states, a set of actions. There's some initial states. The initial state that we're assuming is going to be fixed, S1. We have a transition function, so this function is going to tell us what's the distribution on the next state given every state and action. There's a loss function that's assigned to each state and action. It's between 0 and 1. And our goal is to learn a policy, and this work we're usually going to mostly going to talk about what's called Markov stochastic policies, which are functions from the state to a distribution on actions that we're going to play in that state. And our goal is to choose a policy as to minimize, the expected cumulative loss. Okay, so the model is this. We start from the initial state, we choose an action, then we suffer the loss that's assigned with this state and action. And then the next state is going to be sampled according to the transition function. Okay, so we're advancing to the next state, and then we're going to choose another action, and so on. At every time step, we're going to suffer some loss. And we want to minimize the expected cumulative loss on the trajectory of the gem. So a very important quantity is in the Markov Decision Process is what's called the value function. Before I'm going to explain what the value function is, I'm going to say what is the Q function. So the Q function for a policy is a function from state and action that's going to, at time, is going to tell me what is the expected cumulative loss if I start in this state, choose this action, and after that I'm going to play according to the policy type. Okay? And this function satisfies what's called the Bellman equations, which is the Q function is the current loss in the state and action plus the expected cumulative loss from the next state. Okay, and many times during the slides, I'm going to write it in sort of vector forms. It's going to be like P times the value in the next state, in the next time step, at the current state and action. And the value function for a stochastic policy is just the sort of expectation over the action in the Q function. So this is, in other words, this is the expected cumulative loss if I play according to pi from the current state. Okay? There's also what's called the Bellman optimality criterion, which basically says that the optimal policy, depending on the specific NDP, but here it's going to occur. So the optimal policy is what's called Markov deterministic, so it's going to be greedy according to its own Q function. Okay, so it's going to, at every state, it's going to choose an action as to minimize the Q function in that state. Okay? And usually, in finite horizon Markov decision processes, you can find the optimal policy and the optimal Q function using dynamic programming. Okay, in polynomial time.
In the horizon.
In the horizon, the number of states, the number of actions. So far I just talked about planning. So far we knew the model, we knew the transition function, we knew the loss function. Now I'm going to talk about the learning from relational problems. So in reinforcement learning, we have this Markov decision process, but we don't know the loss function or the reward function, and we don't know the transition function. Okay, and we want to be able to sort of learn it under different kinds of learning models. Here we're going to talk about what's called on-policy learning. Okay, so we're going to choose a policy, and then we're going to observe the trajectory and the losses that our policy generates. Okay, so we're going to run for capital K episode. And at each episode, our agent, the learning agent, is going to choose some policy, and then it observes a trajectory from the MDP, okay, which is just the set of all the states, action, and the observed losses. Okay, and the goal is to minimize the regret, which is the sum over the episodes times the value function, so the expected cumulative loss of this is supposed to be the other way around, because we're in loss, not reward. This is the regret is the expected cumulative loss of our policy minus the expected cumulative loss had we played the optimal policy at all times. Okay? So we're going to basically compete with the optimal policy. without knowing the MDP. So what? Yeah.
We know the optimal policy?
No, we don't know. We don't know the parameters of the MDP. We don't know the loss. We don't know the transition function. So we want to be able to sort of learn the model as we go from the trajectories that we observe. Okay. So let's to approximate the optimal policy. So when people talk about reinforcement learning in this learning model, the main challenges are how do we obtain polynomial regret and sample complexity, and how do find an algorithm that's also like some polynomial runtime complexity, and this comes down to what's called the exploration versus exploitation dilemma, which is, since we only observe the trajectories of the policies that we choose, we need to, on one hand, collect information from the MDP. Okay, so we want to sort of try different kind of states and actions so as to not miss the states and actions that the optimal policy is going to choose. But also because our criterion is regret, we want to at every episode use the information that we already collected as to get low regret. Okay? So for tabular MDPs, where the number of states and the number of actions is finite, we know the optimal regret up to logarithmic factors, which is the horizon, root the number of states, number of actions, number of episodes. This is the optimal rate. Okay. So the common technique in MDPs for achieving this kind of optimal trade-off between exploration and exploitation is what's called the optimism in the face of uncertainty. It's a good principle for life, and the idea is that if our losses are drawn IID at every state of action, then we can maintain estimates of the loss at each state and action and confidence bounds around these estimates. So we know that with high probability at every state and action, the optimal transition, the true transition function, the expected loss is going to be in this set. Okay, and the sets shrink every time we visit this state and action. Okay, so given these confidence sets, we can build the empirical MDP, okay, using these estimates of the expected loss and the transition function. But at every loss, we're going to add some bonus that's going to scale inversely with the number of times that we visit this state and action. Okay, so it's going to go down to 0 as we visit this state and action more and more and more. And given this MDP, we're going to solve and obtain some policy. Then we're going to run this policy in the true MDP. And what's going to happen, given this empirical MDP, the value of the optimal policy in this empirical MDP is going to be the reverse. At most, the value of the optimal policy in the true MDP. This is the idea behind optimism. So now the regret at every time step is going to be at most the regret of our policy once in the true MDP and another in the minus in this empirical MDP with the bonuses minus the value of it in the true MDP. So now we only sort of rebound the regret with something that depends only on the policy that we chose. And this is something that we can control because we choose this policy. So this is important. And one can show that, so with high probability, this is bounded by the sum of the bonuses on the trajectory of the policy that we generated. And as these bonuses decrease every time we visit some state and action, this is going to decrease over time, and the rate in which it decreases is roughly 1 over the number of episodes, the current number of episodes. So if we sum this over the number of episodes, we get Wood's capital K. Okay. So, so sort of the holy grail in RL, which has been sort of the same since the 80s, is what's called functional approximation. And the idea is that in real life, the actual problems that we want to solve RL with are usually huge. So the number of states is usually either infinite or it's finite, but it's extremely large. And we want to be able to obtain sample complexity bounds or regret bounds that do not depend on the number of states. And if the number of actions is finite, you can always get a regret which is exponential in the horizon. It's very easy. You just sample the action uniformly at random, and after exponential number of episodes, you're going to magically choose the optimal policy. You just guess it, and so you can learn basically any policy like this. So you can learn in time that's exponential in the horizon, but we want to be able to obtain polynomial bounds, right? We want to be able to run it in actual machine. So the solution is to incorporate some sort of prior knowledge that we have about the MDP. And the idea, you can do it in many different ways, but the idea behind functional approximation is that there's some function plus f, and the MDP, the losses in the dynamics, or some other quantity of the MDP, can be represented by some function in this function. Okay, and you can think of the function as being linear functions or a neural network or whatever function constitutes. Okay, usually in practice, like what they do in DeepMind, they use neural networks, obviously, but we can the state of the art in terms of theory is that we only know how to solve tabular setting and the linear setting. That's basically it. And the main research that I do is try to sort of push this boundary and understand more complex function classes. But before that, we want to understand the linear setting first. So in linear Markov decision process, with linear functional approximation is that for every state and action, we have some vector representation, phi of S and A. Okay, it's going to be d-dimensional, and the loss is going to be linear in this phi of S and A. Okay, so there's some vector G such that the loss at S and A is the dot product of phi of S and A and G. Similarly, the transition function is also going to be linear in phi of S and A. So we have for every state S prime, there's some vector psi of S prime, okay? And the probability of transitioning from S and A to S prime is the dot product between phi of S and A and psi of S prime. So what you can show is that for the optimal policy, the Q function is also linear in phi of S and A, okay? And this is very important because once we if we have this vector W pi star, even though the number of states can be uncountably infinite, we can still, once we get to some state, we can still calculate the Q function for every action in the state and minimize it, and so we can sort of run the optimal policy in this way without actually representing it as a policy. Okay? So this setting with unknown dynamics and stochastic losses was studied in this paper by Jin et al. And they show a regret which is polynomial in D, the dimension of the linear representation, the number of actions, the horizon, and its root of K, which is 4. Okay. Just as a side note, the regret shouldn't really depend on the number of actions here, okay? But this was sort of improved later with bilateral data work. Okay. So now let's talk about the setting that we consider in our paper, which is linear NDP, okay, with unknown but fixed dynamics, linear dynamics. And so before the interaction starts, we have two options, either the stochastic bandit feedback or the adversarial transformation. So option one is the adversarial information, in which the environment sort of a priori chooses these vectors g1 to gk, which are going to represent the loss at every episode. And in the stochastic bandit feedback, the environment chooses the expected loss, which is some fixed vector g. And now at every episode, the learner chooses some policy pi k. It runs it in the actual MDP and observes the trajectory. And then in option one, the adversarial information is going to suffer the cumulative loss in this trajectory, and then observes the g of the current episode, the actual vector. And in option two, it's going to suffer some sum of L of h, such that L of h is some random variable, some bounded random variable, which in expectation is the loss. So it's phi of shah times g. And it's going to observe all this L1 to LH.
Why is option one called adversarial if G1 to GK were chosen in advance? Like if G2 etc. were chosen based on my policy in the previous one, that's really adversarial. But if they were all chosen in advance, in what sense it's still adversarial?
So this is what's called an oblivious adversary. So it's an adversary that sort of ignores the randomness in your algorithm. So if the algorithm is completely deterministic, then the adversary can sort of know what you're going to do and then choose some very bad sequence for you. But you can think of like more complex adversaries, but
it's sort of an intermediate level of adversary.
Yeah.
Can you say a few words about the relationship with dynamics and LQR?
Completely unrelated. LQR is a much easier setting. At least in the stochastic case, the fact that you have noise in the dynamics that's sort of isometric, it sort of gives you some level of exploration for free. Here you have to sort of work to get exploration. It's linear, but it doesn't have this kind of special structure that LQR has. No. It's the linear MDPs. Okay, so when the Gene paper came out, we all looked at it and said, "Why is this interesting?" Linear MDPs, you can't do anything with it in practice.
And then we decided, okay. So
then we decided that it has. In order to solve it, you need to solve like some complex technical problems that you're going to solve in the general function approximation case. So there are a lot of problems here so we want to kind of use linear MDPs as a stepping stone towards something that's more complicated. And this is what I'm going to present here is an oversimplification of what's going on in the actual paper, but it's extremely complex. It's much harder than the tabular setting. I hope I can give a flavor of it, but maybe later offline.
But isn't this really universal because it's thinking arbitrary functions? The linearity here isn't really, it's not a real restriction. Any dynamics you can.
So the problem is that you're going to depend on in the regret on the dimension. That's the problem.
And he's also using the same function for transition and something else.
The loss in the.
Yes, but it's beginning.
There's a dependence on the dimension, makes it meaningless. The universality is.
You can always like apply like an RBF kernel, but then you're going to be exponential to the dimension. It's not going to help much. So since this paper came out, there's been a lot of work on linear LPTs. So Gene et al. They consider stochastic losses with bandit setting. They give a computationally efficient algorithm with root-key regret. Since then, there's this Noy et al. Paper with adversarial losses, which also gives root-key regret. Recently, very recently, there's this paper by Liu et al. And they give two algorithms for the adversarial bandit setting. One which is not computationally efficient and gives the optimal rate of regret. And the other, which is computationally efficient, gives k to the 3/4. And this is the best that we know in this setting so far. So in our work, we wanted to, this is the actual setting that we wanted to solve, but in order to solve it, we need to solve some technical problems that we didn't really know how. So as an intermediate step, we consider the full information setting, and even here we made some progress. And this setting was, for some reason, never considered before, and so we show the optimal regret here as well.
It makes sense. If the linear bandit assumption is very practical, with the full information, it's extremely.
Like I said, we're not trying to solve this problem to solve some practical problems. We want to solve it because we want to understand the general setting, and even here it becomes very, very difficult. Of course, we wanted to solve function approximation with neural networks, but it's very hard. Like, you can't publish a paper on.
If you commit to the paper, then if you want to take some inspiration, what's going on with function approximation with neural network, then the stochastic bandit is interesting. The adversarial is, I don't know, it's very interesting, adversarial versus the stochastic setup. And the full information adversarial combination, even with neural networks, seems not very practical.
Like I said, we don't really want to solve the adversarial setting to solve the adversarial setting. We're doing it because we want to develop technical tools that we can use later, and even like the tools that were previously developed in adversarial setting are now used in what's called the Oracle sort of literature on RL, and a bunch of other approaches. There's new different ways of doing the exploration versus exploitation trade-off, using convex optimization and stuff like that, which we kind of hope that we can sort of develop further.
Let me maybe rephrase concern differently. I understand the need to sometimes narrow down developing its own, but do you have any intuition of why it needs to build full information will be useful in the non-full information?
Yeah, but this is kind of jumping ahead. You'll see that, first of all, the dynamics in linear MDPs, if the number of states is infinite, you have like basically infinite number of parameters that you want to estimate. So this is something that you can do, but what you can do is estimate the expected value function from a certain class of value functions. But this is really like jumping ahead a bunch of slides. So now you need to build some sort of class of policies that you're going to use during the algorithm. And the way that you choose the structure of the policy is going to affect the way that you can estimate the dynamics. So if you can do it better, even in the full information setting, it's going to help you in the bandit. Okay, I hope this is clear. Maybe we can take it offline later. Okay, so this is the algorithm. The algorithm starts by doing some what's called a reward-free warm-up, which is just basically just estimating the dynamics without the loss for root k episodes. Okay, this is based on this paper by Wagenacker. Then we're going to construct this matrix lambda 0 using the samples that we got from the reward-free warm-up, and construct this set of states for which this quantity is smaller than some 1 over beta. Okay, so this is basically these are the states that were sort of sufficiently explored during this warm-up step. Okay, so for the rest of the episodes, we're going to do the following, and we're going to explain later on. So we're going to choose a policy, play it, observe the trajectory, and the loss function. Then for every time step h, starting from the last to the first, we're going to compute an optimistic version of the Q function, okay, which is this using the dynamics that we estimated. And we're going to set it to 0 if the current state is not in this set of sufficiently exposed states. Okay. Then using it, we're going to compute the value function, and then update the current policy by multiplying it with e to the minus eta times the Q function, and then normalize it to the distribution. Okay. This is the algorithm. It's going to be much clearer later on. Now I'm going to sort of build it sort of step by step and show you how we came up with this framework.
So just a question, I'm not sure for the notation. Is phi fixed or
Fixed and known.
Okay, so in the dynamics you do know some part of it, some sense. But before you even start. Because the transition depends on. So it's not completely unknown.
You don't know the.
You know the feature.
Yeah, you know the features, but you don't know the. You don't know these.
Oh, okay, just confirmation.
There's another model. I forgot the name, but it's basically where you also don't know the fees, and there's the results that show that you can't plan in polynomial time. Okay, so what we prove is that in both of the settings that we consider, we show the graph which is polynomial in h, log number of actions, the dimension, and root of k. The algorithm also runs in polynomial time per episode. And as a corollary, we also have a sample complexity of 1 over epsilon, okay, in the stochastics. Okay. So, I don't know how many of you are familiar with online learning. So Moshe talked about it a little bit before, but basically the main difference is that instead of learning from a training set, building a classifier or whatever, and then we can use it from now on for all times. In this model we have sort of sequential learning, so we have to make a prediction at every time using the data that we've collected so far. And also the losses that we suffer are sort of generated by an adversary. They're not drawn IID from some distribution, so there are no distribution assumptions. So one setting, or a classic setting in online learning, is what's called prediction of expert advice, where we have n experts that say that you want to predict the weather tomorrow. Okay, so you ask these n experts, and each one will tell you what they think the weather will be like tomorrow, and then you sort of want to aggregate all of their advices and make your own prediction. So here at each round, we're going to choose one expert and then follow their advice. We have some adversary. This is nature that sort of knows what the real weather is going to be like tomorrow. So they assign a loss per expert per round, and then after we make the prediction, the losses are revealed to us, and in the end, after T rounds, we want to be able to sort of compete with the best expert in hindsight. Okay? Classic algorithms in online learning, it's hedge or duplicative weights, or has a bunch of names, where there's a parameter learning data. We're going to basically maintain a distribution of the experts, and at every round we're going to sample from this distribution. So it's going to start from the uniform distribution of the experts. So in each round we sample the current expert from the current distribution. Then we observe all the losses of all the experts and suffer the loss of the expert that we chose. And then we update this distribution by multiplying all the probabilities. So it should be e to the minus eta times the loss of each expert, and then normalize it to a distribution. And you can prove that for a proper choice of eta, the regret of this algorithm is root t times log the number of experts. Okay? Root number of rounds, log number of experts. So policy optimization algorithms started by this paper by Daphna. They build on this idea of hedge, and you can think about it this way: in a tabular MDP, in each state you basically run a copy of hedge, and the losses are going to be the Q functions of each action. Okay, so in each episode we play the current policy, observe the loss function, and then for each time step, starting from the last to the first, we're going to compute the Q function of the current policy, and also the value function, and then we're going to update the policy in each state according to this hedge update. Okay, and you can prove that this gives root k regrets. Why is this true? So because we run a copy of hedge at every state and time step, the regret at every state compared to the action of the optimal policy is the number of rounds, which is the number of episodes, k, log the number of experts, which is the number of actions. But now, because the losses are not between 0 and 1, the Q functions are between 0 and h, so regret scales with h. Okay, this is just an upper bound of the Q function. Then we're going to use a very important lemma in LL. It's called the value difference lemma, which lets you compare two value functions of two different policies. And what it says is that if you this difference is the expectation over the trajectory that's generated from one policy, and then you look at the value of the other policy minus the Q function of this the policy that you run the trajectory. Okay. So this basically says that the difference between the value function, you can estimate it using basically looking at what happens at every state if you diverge from this policy and play the other policy in this state and then play the first policy again. Okay, so here we compare the policy that the algorithm chose minus the optimal policy, and this is the expectation with the optimal policy, which is fixed. Okay, and we look at the difference between the value of the Q function of the, and this is the value of the policy that the algorithm chose, which we know. Okay, we don't know the value of the optimal policy. And then the regret is the sum of the number of episodes of the value of our policy minus the value of the optimal policy. Using this value difference lemma, we can write it as the sum over the episodes, sum over the number of time steps, the value minus the Q of the policy that we chose, which in expectation of the trajectory generated by the optimal policy. But since this is fixed, we can sort of just write it as the sum of the number of steps, expectation, then for each state and action, sum over the number of episodes, which is just the regret in this specific state. And this, since we run hedge at every state, is bounded by this quantity. Okay, and summing it over the horizon, we get the regret, which is h squared root k log n. Okay, this is the idea. Okay, so the next step is
just a question.
Yeah.
What is the equivalent of the T experts and the T experts and experts here? The different policies that you are considering?
No, it's the actions. So you run hedge, a copy of hedge at every state. Okay, so you have S times H copies of hedge, and every expert is an action.
Okay.
Okay, and the loss is the Q function of S and A at every state action. Okay, so the next step is to consider policy optimization in unknown entities. Okay, this was done in this paper by Shami et al. So here at every episode we run basically the same algorithm as before, except that we maintain some empirical estimate of the dynamics. Okay, and then instead of feeding the Q function, which we don't know how to compute, we feed this kind of optimistic version of the Q function using the empirical dynamics, but we add this bonus which allows us to explore. So what you can prove is that at every episode, for every state and action, the difference between the empirical dynamics and the true dynamics is upper bounded by the choice of a bonus over H. Okay, the bonus of upper bounds this difference. Okay, and now because of this result, you can plug that into the definition of Q tilde. So on one hand, we have the Q tilde is upper bounded by the loss plus the true dynamics times the optimistic value function. Okay, but it's also lower bounded by the same thing minus 2 times the bonus. So instead of 1 time, the bonus appearing 1 time, so we double it. And then they have this sort of extended value difference lemma, which lets you gives you a representation of a difference between value functions that are not necessarily from the same policy and not from the same dynamics. Okay. So we have this term as before, but now we have this additional term that sort of quantifies how much the Q tilde that we use is an actual dynamic, is an actual Q function in the NDP. So you have this loss plus the true dynamics times the value minus the Q function. Okay, and And now we can, and now we need to use this lemma twice. Once for the policy played by the algorithm, and once for the optimal policy. So first for the policy played by the algorithm, this term is 0 because the expectation over the action of Q tilde is exactly the value function. Okay. And this term, because of this lower bound, is here it's almost 2 times the bonus. So if we sum this difference between the true value function and the estimated optimistic value function of our policy, we can upper bound it with just with the sum of the bonuses over the trajectory generated in the policy. And this you can prove is summed up to roughly h times roots and number of states, number of actions. Okay. So this is what we sort of pay for not knowing the dynamics on the policy that we chose. So now we're going to use this lemma again to upper bound this difference. So this is the difference between the optimistic Q function, the value function, and the true value of the optimal policy. So now we have these 2 terms, but now they're in expectation over the optimal policy. Okay. And now this term, because of optimism, is at most 0. Okay, so we can discard it. And the sum over the number of episodes of this difference is at most the regret of the algorithms times h, which is the same as before. So overall, the regret is the sum of these 2 terms, which is roughly h squared with the number of state convergence. Okay. So lastly, we need to talk about what happens in linear MDPs. So in linear MDPs, there are 2 differences. One is that the empirical dynamics are now they have an infinite number of parameters, but they have this linear representation. So we need to estimate it using least squares, not just by counting how many times we use it as every state action. But now because we're using least squares, and least squares produces estimates that are not bounded by they can be bounded by k, but we don't want to be bounded by k. We want to be bounded by the parameters of the MP. So, but we know that the actual Q function is between 0 and h, so we can just sort of clip it to be between 0 and h. Okay? And then the algorithm runs as before. Okay, so this scheme with a bunch of other additional components in the bandit setting gives a regret of k to 3. So let's talk a bit about estimating the dynamics. So in the tabular setting, it's easy. You sort of count how many times you visit every state action and how many times you visit this state action, and then transit to some state as prime. And then this ratio gives you an estimate of the probability of the transition. And you can prove that with high probability, for every state action, the empirical dynamics approximate the true dynamics, but it's something that scales like root the number of states over the number of times you visit the state action. So obviously we can't use it for linear MDPs because of this dependence on the number of states, which is a big problem. So in linear MDPs, we need to utilize the linear structure, but the number of parameters here is d times s. Okay, so this is a big problem. You can't represent the actual dynamics themselves. Okay, so there's lots and lots and lots of parameters that we need to estimate. So, and the solution here that was presented in the Jean et al. Paper is that instead of estimating that all of the parameters in the dynamics, we're going to estimate the expected value of the value function from some policy class. Okay, so not all of the value functions, but just the value functions of policies that are of interest to us. And this is not a big problem because we know that the optimal policy is greedy with respect to some linear function. So the optimal policy has this structure. So if we build this policy class, for example, on greedy policies that are greedy with respect to linear functions, then it will include the optimal policy. And this policy is kind of represented by only d parameters. So there's so it's much smaller than if you consider all possible policies. So now you can think of the dynamics as this kind of big D times S matrix. Okay, so for each state S prime that we transition to, there's this vector psi of S prime. Okay, as a column. Okay, and you can sort of then solve it using estimate dynamics using Rich regression. Okay, so if you know you're in some state Si and action AI, if you multiply it by this matrix C, you know it's supposed to give you the entire distribution over the next state, but you only know that you transition to state Si plus 1, so you kind of approximate it using some one-hot vector over the state Si plus 1. Okay. And what's nice about this is that there's a closed form solution to this regression, which is of this form. So there's this matrix lambda inverse times sum of phi of Si and AI times this one-hot vector over Si plus 1. And this matrix lambda has this, is a D by D matrix of this form. So even though this matrix C that we estimated is this D times S matrix, it only has n non-zero columns. Okay, so we can still represent it so with polynomial number of parameters. Canonical, yeah. So because of the kernel trick, we can always sort of compute the p times any value function using phi times this vector v hat, and v of hat is just the this matrix C times the value function, which is of this form. Basically, so now you only need to sort of get an estimate of all these vectors V for all of the value functions of the policies that you're interested in. Okay, so Jean et al. Show that if your policy class has a low covering number, then basically you can approximate these vectors in norm matrix norm lambda by something that's polynomial in the dimension h and the log of the covering number of your policies. So now our goal is to find some policy class that whose log covering number is something that's d, h, something like that, doesn't depend on k. That's important. So back to our algorithm. Our algorithm plays policies that look like this. They're the probability of choosing an action every state is something like e to the minus eta sum of these q tilde functions that we generate. Okay, this is the policy that the algorithm chooses. Now we know that the optimal q function is linear. So if we sum this linear function, we still get a linear function. Linear function has the parameters, so the covering number is small. But on the algorithms that people considered before, because of this clipping, basically you lose this linear structure, and so you need to. So now you have k parameters instead of d parameters, and this is a problem. Okay, So basically, our solution is to use this reward frame warm-up in order to get a good enough estimate of all the Q functions that we're interested in, and so remove this clipping completely. Okay, so the clipping, if you think about it, when is this estimate is large? When we sort of didn't explore S and A much. Okay, so only then the clipping will be active. If we explore all the state of actions before we generate these estimates, then we don't have to use clipping at all. And indeed, we proved that in our algorithms for all episodes, for all times, for all of the states S and Z, we have this bound on the expectation of the next, the value in the next step. And this is upper bounded by some quantity that depends on phi of SNA and the matrix, the lambda k, the matrix that we obtained by these squares in this specific episode. So the reward-free warm-up comes from this paper by Wagenmaker. We run it for root the number of episodes. And the problem is that in linear MDPs, because the state space can be infinite, you can't ensure that you're going to explore all of the states. But you can ensure that you're going to explore most of the states. So basically, using this this algorithm, what it gives us is this estimate of the dynamics, such that if you look at the expectation of the value function with respect to the true dynamics minus the empirical dynamics, this is phi of SNA times the difference between these V vectors, and this is going to be upper bounded by phi of SNA in this lambda 0 inverse norm times something polynomial in H, and because the way that we chose this set Z, this is at most 1 over beta, and beta is D times H. So this is, all in all, this is something that's polynomial in H. And also, what they show is that for any state not in Z, the probability that any policy is going to choose it is at most epsilon cov, and epsilon cov that we chose is 1 over root k. Okay, so it doesn't matter which policy you're going to choose. You're not going to observe the probability that you're going to observe the state is at most 1 over root k. Okay, so let's recall the algorithm. So the algorithm starts with this warm-up. This warm-up allows us to limit the scale of our Q estimates. And then it runs a policy of this policy optimization scheme, during which for the Q functions that we generate, we set them to 0 if the state is not in the set of states that's sort of well explored. Okay? So as you might guess, if the state is in Z, then we have a good estimate. If the state is not in Z, then the probability that we're going to visit it is it's most 1 over root k, so it's not going to cost us this much. שאלה טובה. יש לי ממש 2 שקפים אחרונים. זה בסדר. So basically the proof goes by using this extended value difference lemma. We have we have 4 terms. The first term is sort of the cost from traversing the states that were not explored during the warm-up, which is because of our choice of epsilon cov as most root k. Then we have the cost of misestimating the dynamics on the policy that we chose, which is at most the sum of the bonuses, which is root k. Then we have the cost of hedge, which is root k, and an additional term, which is at most 0 because of the optimism scheme. So this is basically it. So to conclude, we're the first to show root k regret in the full information setting. We plan to use it as a stepping stone towards obtaining a polynomial time algorithm for the bandit adversarial setting. And for that, we needed to build some new technical tools. So for future work, we indeed plan on working on the bandit setting, but also like what we're interested in basically a statistical question is that all of the problems they all come from the fact that we have to use least squares to estimate the denotes. So the question is whether there's a different estimation method that's not least squares that's going to give us maybe a proper linear dynamic which is bounded and has maybe nicer properties, and then maybe there's an easier solution to this problem. And that's it.